Hi, in this particular conceptual video, we are going to learn the concept of the dead space. Now, before we actually discuss the physiology of the dead space, I would like to express my opinion, a personal opinion, that is, it shouldn't have been called as dead space. No space in the body could be called as dead space, the space in a living body. It would be called as non-respiratory space because it does not allow the gas exchange to occur. But it performs lots of functions, humidification of air or the so-called air conditioning. It helps in the speech and so on and so forth. So it's not really a dead space. It is a non-respiratory space. So let's try to understand what is this dead space and what is the concept behind it, what is the significance of this dead space. If we look at the respiratory passage, trachea, it divides into right and left main bronchus. So trachea is taken to be the 0th generation of the respiratory passage. And then as it divides into right and left main bronchus, that's the first generation. And then the passage divides and redivides. These are called as the generations of the respiratory tree. So such 23 generations exist for the respiratory passage. This is just a diagrammatic representation. Now from the trachea onward, the first 16 generations are said to be the conducting zone. That is, they are meant to just conduct the air, inspired air and expired air. So they are the conducting zone, and the last 7 generations are called as respiratory zone. That means trachea dividing into bronchi, main bronchi, and then bronchioles, dividing up to terminal bronchioles. Up to the terminal bronchioles would be the conducting zone. Now beyond that, there are respiratory bronchioles. Respiratory bronchiole, the atrium and the alveolar sac. That would be called as the respiratory zone where gas exchange occurs. So first 16 generations, conducting zone, last 7 generations, respiratory zone where actually the gas exchange occurs. And therefore these first 16 generations are said to be the dead space or the non-respiratory space. Why it is non-respiratory space? Because it does not have a suitable epithelium so that the gas exchange could occur. I mean, oxygen from this space could directly enter the bloodstream. That's not possible. So that's a non-respiratory space or a dead space. Conventionally, its volume is taken to be 150 ml. However, that's a very generalized figure. To be more precise, the dead space volume is said to be 1 ml per pound of the body weight. That's a more appropriate way of denoting the dead space, because it cannot be 150 ml in each and every individual. I mean, imagine a small baby, newborn baby, the size of the airways for that small infant, and an obese adult, the size of the airways for that adult. It would be different, and therefore the volume of the conducting zone, volume of the dead space would be different, and therefore it is mentioned as 1 ml per pound of the body weight, and therefore in a 70 kg healthy adult, 70 kgs would be roughly 150 pounds, and therefore 150 pounds, 150 ml would be the volume of the dead space in an average adult. So that's taken as the volume of the dead space. What is the disadvantage of the dead space? Of course, this dead space is disadvantageous. What are the disadvantages? There are 2 disadvantages of this dead space. One for the inspired air and one for the expired air. Dead space is disadvantageous for inspiration as well as expiration. Let's see how. Let's start with the inspired air, disadvantage to the inspired air. This is the airway, or rather the airways, the conducting zone, and finally the respiratory zone. Just a diagrammatic representation. Now consider that our tidal volume is 500 ml. We are going to inspire 500 ml in, let's say, 3 seconds. As we start the inspiration, the air starts moving in. It goes through the dead space and it reaches the alveoli. The gas exchange is going to occur in the alveolus, or rather across the alveolus. Now what happens is, of the total 500 ml that we inspired, all of it is not going to reach the alveoli. It's not going to take part in the gas exchange. Imagine out of those 3 seconds that we inspired, last part of the inspired air will stay in the dead space. Last part of the inspired. Imagine we did inspiration for 3 seconds and at the end of those 3 seconds, inspiration stops abruptly. What happened? 350 ml, first 350 ml would have reached the alveoli. So that will take part in the gas exchange. I mean that oxygen would be available. But last 150 ml, we are assuming here the volume of dead space to be 150 ml. Last 150 ml of that inspired air would stay in the dead space. And inspiration has stopped and the expiration will start. That means the last 150 ml stayed in the dead space. It never reached the alveoli. Inspiration ended and expiration starts. That means first part of the expired air would be the last part of this inspired air which remained in the dead space. So what happened really is that out of the 500 ml that we inspired and the oxygen present in that 500 ml air, all of it is not made available to the body. 150 ml is wasted because it stayed in the dead space. So for the inspired air and for the oxygen that could be made available to the body, this becomes a handicap, it becomes a deficit. That's the disadvantage of the dead space so far as the inspired air is concerned. Almost 1/3 fraction is not available and its oxygen is not available to the body. That's the first disadvantage of the dead space. But remember, last part of the inspired air, this is important, last part of the inspired air is going to stay in the dead space and inspiration ends, and then when expiration starts, immediately the first air to come out will be from the dead space. This air will be the first to come out, which is the last part of the inspired air, and then later on alveolar air will come out. So first disadvantage for the inspired air, that almost 1/3 of the oxygen that could have been available is not available. It's never reaching the alveoli. It's remaining in the conducting zone. Now coming to the second disadvantage, disadvantage to the expired air. How this is a disadvantage to the expired volumes? Now, expiration is for what? Expiration is for removal of the blood gases. I mean, carbon dioxide from blood, it enters the alveoli and from there it is going to be expelled out. So expiration is really for removal of the blood gases. Even here the dead space is disadvantageous. Why? Because we inspired 500 ml, we also exhale out the 500 ml of air. That's our tidal volume of expiration. So we would have liked that 500 ml that is being exhaled out, all of it is coming from the blood gases. I mean, it is carrying the blood gases. It is removing the carbon dioxide from the blood. But no. Remember, first 150 ml that comes out is just the atmospheric air the last part of the inspired air that never reached the alveoli. It is this air which is coming out first with the expiration. It was the last part of inspired air, means it's not coming from the blood. I mean, it's not coming from the alveoli. It's not carrying the blood gases. It's therefore only the last 350 ml out of the total 500 ml that we exhale out. Last 350 ml is coming from the alveolus. That is, it is removing the blood gases. It is exhaling out the carbon dioxide. So we could have removed 500 ml air from the alveolus, and that could have removed more amount of carbon dioxide. But for the fact that out of the total 500 ml, first 150 is just the dead space air which never reached the alveoli, and only the last 350 ml is coming from the alveoli, and it is carrying the blood gases, carbon dioxide normally. Now imagine how this becomes a disadvantage. Imagine a gas poisoning, carbon monoxide poisoning. Now in the condition of gas poisoning, let's say carbon monoxide poisoning, we would want to remove the carbon monoxide or the said gas from the blood. And if the exhaled air was all 500 ml was coming from alveoli, then it would have carried more blood gas. It would have carried more of that gas which came from blood into the alveolus and is coming out. But all of the 500 is not coming from the alveolar air. I mean, only 350 ml is actually carrying the blood gases and is coming out. So even for the removal of the blood gases, dead space becomes a disadvantage. That only 350 ml with each breath is carrying the carbon dioxide or any blood gas that we are referring to here, and not the entire 500 ml that we would have liked, that it is entire 500 ml of the exhaled air carrying alveolar gas, which is actually the blood gas which has come into the alveolus. So that's a disadvantage for the expired air, that for the removal of blood gases, this dead space becomes a disadvantage. So that's significance of the dead space. There are various conditions which can increase or decrease the dead space. But before that, let's try to understand the types of dead space. There are two types of dead space. Even this nomenclature, it is little confusing. There is anatomic dead space, which is the first 16 generations of the respiratory tree. That's called as anatomic dead space, because anatomically that part is a non-respiratory part. As we have discussed, trachea, bronchi, bronchioles, there is no respiratory epithelium or suitable epithelium for gas exchange, and that part is therefore the anatomic dead space. Second type of dead space is called as physiologic dead space. That is, functionally that part is not taking part in the gas exchange. So we can call it total dead space. Instead of calling it anatomical and physiological dead spaces, let's say first 16 generations are anatomic dead space, fine, that's mandatory, it's going to be there. But total dead space would include anatomic dead space plus the non-respiratory gas exchange areas. Let's put it simply as alveolar dead space. Anatomic dead space plus alveolar dead space. What do we mean here is that all the alveoli are expected to function normally, and all the alveoli are expected to take part in the gas exchange. But if some of the alveoli are not taking part in the gas exchange because they don't have perfusion to them, then it becomes an alveolar dead space. Well, ideally, it would have been called non-respiratory gas exchange areas. The gas exchange areas include respiratory bronchioles as well. But just to simplify it, I'm putting it this way: alveolar dead space. So, physiologic or total dead space, functionally dead, would include anatomic dead space, which anyways is not taking part in gas exchange, and the alveolar dead space. Normally, the anatomic and physiologic dead spaces are expected to be identical. That is, all the alveoli are expected to take part in gas exchange. They should be fully functional. But if for some reason, like there is no perfusion to the alveoli and they don't take part in gas exchange, that would be considered to be a wasted ventilation. That is, inspired air did reach the alveolus, but there is no blood perfusion, and therefore it was a wasted ventilation. It did not take part in the gas exchange. So that is the total dead space or physiological dead space. These are the two types of dead space. Now, there are certain conditions in which the dead space can increase or decrease. For instance, let's say deep and forceful inspiration. Deep and forceful inspiration. Anatomic dead space may increase, but physiologic dead space or alveolar dead space would decrease. Anatomic dead space can increase slightly with deep and forceful inspiration. How? Because deep and forceful inspiration creates a traction over the trachea. There is a traction over the trachea, and its volume can actually increase. So, volume of the respiratory airways can slightly increase with forceful inspiration, and therefore volume of the anatomic dead space might slightly increase by 10%, 15%. But alveolar dead space will decrease, and therefore physiologic dead space may also slightly decrease. To be precise, the alveolar dead space can decrease because some of the non-functioning alveoli, some of the collapsed alveoli may open up and start taking part in the gas exchange. So, those alveoli which were not taking part, now they have started taking part in the gas exchange. So, alveolar dead space would actually decrease with forceful inspiration. So, anatomic dead space might increase, but physiologic or alveolar dead space might decrease, will decrease with forceful inspiration. So, this dead space is a variable space. It can change, particularly the alveolar dead space and therefore physiologic dead space. Volume of the conducting airways may not change much. So, what is the clinical significance? How can you reduce the dead space? When do you need to reduce the dead space? I'll give you one or two instances. One is tracheostomy. Tracheostomy would reduce the dead space by half. Tracheostomy is an opening is made at the lower end of the trachea and a tube is inserted so that breathing happens from that point onward. So, the extrathoracic dead space is negated. It's not taking part in the process of breathing, and the breathing straight away starts from the lower end of the trachea. So, tracheostomy is done to reduce the dead space and therefore reduce the wastage of ventilation. More and more oxygen thus can be made available to the body in serious conditions, serious disorders. When assisted ventilation is being given, tracheostomy is done in the serious patients. So, it reduces the dead space by almost half. Second is apparatus dead space. Another clinical significance, that patient is being given assisted ventilation, assisted breathing through the apparatus, and some of the space of the apparatus which is delivering oxygen, it may be included in the dead space. It increases the volume of the dead space by a few mLs. So that's called as apparatus dead space. That's a clinical significance and the importance of the dead space. In the next video, we will see how do we measure these dead spaces, anatomic dead space and physiologic dead space.